Some of the most compelling evidence that life could arise beyond Earth is hidden in the stars we barely see, and number one is something almost nobody guesses. Stay tuned until the end to discover the ultimate surprise. Surprisingly, astronomers have detected phosphorus, an essential element for DNA, in the Large Magellanic Cloud, a satellite galaxy 160,000 light-years away. Using radio telescopes, researchers identified phosphine-bearing molecules within dense star-forming regions, suggesting that the raw material for genetic molecules is not confined to the Milky Way. This discovery reshapes our understanding of where life-supporting chemistry can arise, because phosphorus is notoriously scarce in interstellar space. The presence of this element indicates that stellar nurseries across galaxies may share a common chemical recipe. Up next, we'll explore a simple yet profound molecule that appears in a completely different corner of the sky.
Intriguingly, formaldehyde, a building block for sugars, has been mapped throughout the Perseus molecular cloud, a massive star-forming region about 1,000 light-years from Earth. Sensitive observations with millimeter-wave arrays reveal that this aldehyde spreads across filaments where new stars are born, hinting that prebiotic chemistry can begin even before planets coalesce. Scientists believe that shock waves from young stars may liberate formaldehyde from icy grains, seeding the surrounding gas with organic material. This process could seed nascent planetary systems with the ingredients needed for life. Coming up, we travel to a famed nebula where even more complex organics have been spotted.
Astonishingly, the Orion Nebula, one of the brightest star-forming regions in the night sky, hosts a suite of complex organic molecules such as ethylene glycol and methylformate. These compounds, detected through infrared spectroscopy, resemble substances found in comets within our own solar system. Their abundance suggests that the chemistry that later delivered water and organics to early Earth may be a universal byproduct of star birth. Researchers argue that turbulent mixing in the nebula's hot cores drives reactions that stitch together simple carbon chains into larger, life-relevant structures. This paints a picture of a galaxy where the chemistry of life is woven into the very fabric of stellar nurseries. Next, we'll look at the remnants of a dying star that surprisingly contains silicon carbide grains.
Remarkably, remnants of ancient supernovae have been found to contain silicon carbide grains, tiny crystals that can survive the violent explosion of massive stars. These grains, collected in meteorites that land on Earth, bear isotopic signatures indicating they originated outside our solar system. Silicon carbide provides a sturdy scaffold for organic molecules to attach, potentially acting as a catalyst for prebiotic chemistry in interstellar space. While the exact pathways remain under study, the presence of such sturdy mineral seeds suggests that even the most catastrophic events may sow the groundwork for life's chemistry elsewhere. Up next, we dive into a nearby young star system where water vapor has been directly observed.
Unexpectedly, astronomers have captured abundant water vapor spiraling around Hydrae, a young star only 10 million years old and located 196 light-years away. Using ALMA's high-resolution capabilities, they traced water molecules across the disk's inner regions, where planets are likely coalescing. This finding demonstrates that water, a cornerstone of life, can be delivered early in planetary formation, even beyond our own system. Some models suggest that icy grains drift inward, releasing vapor that later condenses onto forming worlds, providing a primordial ocean source. The implication is profound. Water may be a common byproduct of planet birth throughout the galaxy. In the next segment, we'll explore exotic methanol masers that light up the heart of our own Milky Way.
Few people know that intense methanol masers, natural cosmic lasers, flare brightly in the Milky Way's central region, signaling pockets of dense, warm gas rich in organic chemistry. These masers amplify radio emissions from methanol molecules, making them detectable across thousands of light-years. Their presence indicates that complex organics can survive the turbulent environment near a supermassive black hole, where radiation and gravitational forces are extreme. Researchers propose that shock fronts from stellar winds compress the gas, fostering reactions that build larger molecules. This challenges the idea that only calm, quiescent clouds nurture prebiotic chemistry. Soon we'll turn our gaze to a massive cloud where cyanide compounds hint at early Earth-like chemistry.
Deep within the Sagittarius B2 molecular cloud, astronomers have identified cyanide-bearing molecules such as HC3N and CH3CN, which are considered prebiotic because they can lead to amino acids under the right conditions. These compounds were detected via their characteristic spectral lines in radio observations, revealing concentrations far higher than those found in typical interstellar clouds. The dense, shielded environment of Sagittarius B2 provides a laboratory where ultraviolet radiation is limited, allowing fragile molecules to persist and interact. This suggests that the essential steps toward biology, forming nitrogen-rich organics, might occur naturally in massive star-forming regions across the galaxy. Next, we venture to an exoplanet where ammonia has been spotted in its atmosphere.
Surprisingly, the temperate exoplanet K2-18b, located about 124 light-years away, shows spectral signatures of ammonia in its cloud-laden atmosphere. Using the Hubble Space Telescope, scientists identified absorption features consistent with NH3, a molecule that on Earth plays a key role in nitrogen cycles and prebiotic chemistry. While the planet's surface conditions remain uncertain, the presence of ammonia hints at active atmospheric chemistry that could, under the right circumstances, produce more complex nitrogen compounds. Some models suggest that photochemical reactions driven by stellar radiation could sustain ammonia levels over long periods. This discovery expands the catalog of worlds where life-supporting chemistry might be underway. Coming up, we'll examine hydrocarbon chains drifting through the halo of our neighboring galaxy, Andromeda.
Hidden in the diffuse halo of the Andromeda galaxy, astronomers have traced long-chain hydrocarbon molecules stretching dozens of atoms in length. These carbon-rich compounds were identified through infrared emission features captured by space-based observatories, indicating that complex organics are not limited to dense star-forming regions but can also reside in the tenuous outskirts of galaxies. Their survival in such low-density environments suggests that once formed, organic molecules can be transported across vast intergalactic distances, potentially seeding other systems. This widespread distribution reinforces the idea that the universe is a vast chemical reservoir, constantly mixing and redistributing life's building blocks. Finally, we arrive at the most astonishing clue, a rare phosphorus-bearing molecule discovered in a galaxy more than 10 billion light-years away.
Finally, the most unexpected clue comes from the distant starburst galaxy SMMJ 2135-0102, located roughly 10 billion light-years away, where astronomers have identified a rare phosphorus-bearing molecule, PO, in its interstellar medium. Detected via millimeter-wave spectroscopy, this molecule indicates that even in the early universe, shortly after the first generations of stars, the essential element for DNA and RNA was already being forged and dispersed. The presence of PO at such a cosmological distance suggests that the processes creating life's fundamental chemistry began much earlier than previously thought, potentially providing a universal template for life to emerge wherever conditions allow. This revelation ties together the whole list, showing that the ingredients for life are scattered across space and time, waiting to be assembled.
We've traveled from distant clouds of phosphorus to the faint whispers of water vapor in alien disks, each clue painting a richer picture of how life's ingredients may be scattered across the cosmos. If the idea that we aren't alone in chemistry sparked your curiosity, hit like and subscribe so you don't miss the next deep dive list, new mind-blowing discoveries every week. Which of these 10 clues struck you as the most unexpected? Let me know in the comments below. Thanks for watching, and keep looking up.